So in matrix notation, okay, B takes on the form, it has 1s on the diagonals, okay. It has a gamma in the 1, 2 and 2 position, 1, 2 and 2, 1 positions. It also has a gamma square in the 1, 1 position, okay, and the others are all zeros. Okay, now if you look back at our expression for sigma, right, the general expression for the Cauchy stress for isotropic hyperelastic materials, we also need B square, okay. So let's get B square written out, okay. Now B square using our tensor notation is B times B, right, B acting on B, and that is 1, the isotropic tensor, plus gamma E1 tensor E2 plus E2 tensor E1 plus gamma square E1 tensor E1, everything again, right? Okay, and now matrix notation. Matrix notation for B square is, okay, wait a minute, I need to complete this. Sorry, too early to get into matrix notation. I need to write out what B square is, just using tensor notation first. Okay, so when we carry this out, we get 1 plus our quadratic terms are of two types. Well, first let's write out all the linear terms. We get 2 gamma E1 tensor E2 plus E2 tensor E1, okay. That does it for the linear terms, okay, for the terms that are linear in gamma. We then get a few quadratic terms which are of the following form, right? Gamma square, okay. The quadratic terms that we pick up here are the following. We get E1 tensor E1 plus E2 tensor E2, okay, and those two terms come from that gamma acting here, okay, and the remaining quadratic terms are also obtained from right, from this acting on that, right, and likewise that acting on that, okay. But those terms are of the form, right, right, we just add on a 2 here to each of those, okay. Okay, and let me see, that takes care of the, we've taken care of the linear terms, we've taken care of some of the quadratic terms, okay. All right, now I think we've taken care of all the quadratic terms actually. Yep. So now let's look at the cubic terms, okay. For the cubic terms, we get okay, all right. The cubic terms will come from the action of the linear term with that quadratic term. Okay? And when we carry that out, we see that the term that survives here is a term of the form E2 tensor E2. Okay? And another cubic term that survives is from the action of that on that. Okay? And when we compute that term, we get, wait a minute, sorry, this term is E2 tensor E1. Okay, and therefore when we compute the other one, we get a term of the form E1 tensor E2. Okay? All right. And finally, we get a quartic term. Okay, which is from the action of this term on that one. Okay? Okay, so the quartic term then comes from the action of those last two terms on each other, and that takes on the form gamma to the fourth E1 tensor E1. Okay, so let me stare at all of this, and now I realize that I made an error with the quadratic terms. Okay, and that should properly be the E1 tensor E1 term actually gets 3 contributions. Okay, and the E2 tensor E2 term gets only 1. Okay, all right. So after some trials, we've got B square correct. Okay, so now let's put everything together, right? I could go ahead and write this in matrix notation, but it's just going to fill up a lot of, it's going to fill up lots of white space, but nevertheless, for completeness, let's just get it down. Okay, so B square takes on the form. Right, now the diagonals all get 1. The other terms that also show up on the diagonal are, right, we get 3 gamma square on the E1 term. We get gamma square on the E2 term. Okay. Additionally, we get a gamma to the fourth on the E1 term. Okay. The off-diagonal terms, the 1, 2, and 2, 1, both get a 2 gamma plus gamma cube, 2 gamma plus gamma cube. All right, and hopefully I have managed to get everything in place here. I do believe I have. Okay. Now we put everything together. Okay. Now, just for some ease in writing, I am not going to write the general tensor form of these expressions simply because it's going to run into 3 or 4 lines. Okay, let me go directly to the matrix form of sigma. Okay, remember that sigma is alpha naught isotropic tensor plus alpha 1 b plus alpha 2 b square, but I'm not going to say it here, but the alphas are all functions of the principal invariants. Okay, so in matrix notation, right, this takes on the form a form that I will write out carefully as possible. Okay, the alpha 0 multiplying the isotropic tensor is easy. It just gives us an alpha 0 on each diagonal term. Okay, and I'm going to give myself plenty of room here. those are the diagonal terms. Okay. Now we know straight away that all the 1, 3, 2, 3, 3, 2, and 3, 1 terms are 0. So let's just slot in zeros there. Okay. The remaining terms are the ones that we need to fill. Okay. So we've taken care of alpha 0 multiplying the isotropic tensor. Okay. Now let's get in the next term, which is the alpha 1 b. We have b at the top of the slide, which makes life somewhat easier for us. So now let's write that in. So in the 1, 1 position, we get alpha 1 times 1 plus gamma square. Okay. In the alpha 1, 2, sorry, in the B1, in the 1, 2, and 2, 1 positions, we get alpha 1 gamma, and likewise we get an alpha 1 gamma here. Okay. It gives us an alpha 1 in the 2, 2 position as well as the 3, 3 position. Okay. And then we come to b square, okay, which is just alpha 2 times all the b square terms. Okay. So in the 1, 1 position, we get alpha 2 times 1 plus 3 gamma square plus gamma to the 4th. In the 1, 2, and 2, 1 positions, we get alpha 2 times 2 gamma plus gamma cube. Okay, same thing here. And here we get, in the 2, 2 position, we get alpha 2 times 1 plus gamma square. Okay, and finally down here we just get alpha 2. Okay, all right, so that's it. That is sigma. Remembering, however, that alpha 0, alpha 1, and alpha 2 depend on, they're all functions of, right, I would write it out generally as this form, right? They all depend upon the principal invariance of B, right? So those are not just constants. Okay? All right. So we have this form. We'll stop the segment here. When we come back, we will inspect it and see what there is for us to learn from it.